gathered here to welcome Dr. Shaohui Foong for a seminar. I'll just briefly read out. Dr. Shaohui Foong is an assistant professor in engineering product development.
It's quite long, you sure?
I'll stop halfway. At the Singapore University of Technology and Design, as well as a visiting academician at the Changi General Hospital, and was a visiting assistant professor in the Department of Mechanical Engineering at the Massachusetts Institute of Technology, 2011. Prior to that, he did his undergraduate and graduate studies in mechanical engineering at the Georgia Institute of Technology in Atlanta, Georgia, USA. He has a keen interest in mechatronics, which is a synergistic integration of the multiple disciplines of mechanics, electronics, control theory, and computer science. And much of his research is centered around designing and developing novel mechatronic systems for a wide spectrum of applications. That's all for my introduction, and now let's welcome Dr. Shaohui Foong for his talk.
All right, thank you, Haimo. So I'm very happy to be here. So it's actually not my first time in New Zealand. I've been here before for holiday, but it is my first time in Auckland. So I thought it's quite interesting and it's very nice. I think that the winter here is awesome. If you come from Singapore like me, you appreciate the cool weather. I really enjoy the cool weather here. And the air is so fresh. So I think Haimo has done a very nice introduction. My background is mechanical engineering, but right now in research, I think there are no longer disciplines. You actually have to do research in multiple areas. So today I'll actually do it won't be very technical because I wanted to make it more exciting rather than bore you to death with equations. So I'll just talk about magnetic fields, and it's actually it's an interest that has followed me since my PhD work. And I'll show you how my journey through it. And I think most of you will find it quite interesting. So maybe before we start off, maybe we can motivate you a little. When you talk to someone and ask them, what are the important equations that revolutionize the world, right? I'm sure most people will talk about this equation, one of them. You will not fail to come up. Do you know what equation it is, just in case? Which maybe you can tell me? Sorry? Very good, Newton's law. Now the question is which one? Yeah, so Newton has a few laws, right? Maybe you guys forgot some physics too. Exactly, this is the Newton's second law of motion. Right? It governs everything that moves, literally. And of course, this handsome guy is Newton. Right, so some people will say this, and then some people might also, more contemporary people might say this is a really important equation. Right? Anybody know what's this equation? Energy, excellent, but who's the guy who talked about this? Einstein. Right, so this is the energy equation, right? Mass energy. Essentially, it tells you for every mass, it actually equates to energy. And it's related by c squared, which is c, the speed of light. Right, so typically, these are the two equations that most people will say about. Right? Very few people, if you will talk about this equation, very few. But actually, it's just as important as the first two. Anybody has any ideas? What are these? These are the Maxwell's equations, right? Right. James Clerk's Maxwell. Right, so actually, magnetics is actually a very interesting area. I will say it has been overlooked by more exciting stuff like Newton's laws, and just now Newton's laws, and of course the energy equation. But hopefully after today, you'll see a lot more of what magnetics can do. Right. So anyway, some brief history of magnetics is actually one of the oldest things. It actually started in 600 BC when somebody discovered that some magnetic material, lodestones, can actually point to the north. 600 BC, right? But it wasn't until the early thousands of years where they started to use it for compassing. So there's actually a long time before you actually come to here, right? And the four equations came only in 1835. So you can think of it as a very, very long evolution and discovery for magnetics. Right? So anyway, this is a nice summary. Right, so if you were asking what can magnetics do, it can do a lot. Here's only a small subset that I can only squeeze onto these slides. You can have, most people, hopefully you still remember your hard disk drive. Nowadays we do flash storage, but back to the days when you want to store stuff, you had to do magnetic material. Your credit card is also magnetic, right? Storing data, you can usually store data. If you're injured, you need to go to the hospital, the first thing you do most of the time is MRI. Uses magnetics. Right? Then we can go on to actuation. If you take a car, an electric car, you take a train, all those are powered by electric motors, which inside are permanent magnets. Right? Essentially, anything that converts electrical motion to physical motion requires magnetics. Right? But today I want to talk about something more interesting, which is the localization and navigation. Right? So localization is knowing where you are. Right? So this one I won't talk about it too much. Technically, in your pocket, you already have a magnetic sensor in your pocket today. Back then, maybe 10 years ago, this was not very popular, but now everybody has a magnetic sensor in your pocket, and you use it almost every day. Right, so I'm going to focus on localization. Just for those who don't know what localization is essentially to know where you are, right, with respect to known markers. And everybody knows GPS, right? GPS is a godsend. Right, for now, anywhere in the world, as long as you load out a GPS system, you can find out where you are. Amazing. And what it does is it uses satellites that send signal down, and by decoding this signal, you can actually, down to the nearest meter or so, where you are on Earth. Right. So it's quite amazing. So this is, and I'm sure that even if you know this space very well, the GPS helps because you get confident. Even when I go to work, sometimes I use the GPS so that when I drive, I know that the turns I'm taking are correct. Right. So even if you are a very experienced navigator, a GPS always helps. And this was what I thought about it and how maybe you can actually navigate one of the hardest places on Earth, which is inside the body, the human body. Right? People have tried to look inside the body and track where are things in the body, because when you want to heal someone, when you want to insert instruments, you need to be very sure where the instruments are, because any mistakes is life and death. Right? So you can think of it like developing a GPS system for the body. Right? So this is what I have been trying to do for some time. So actually there are, back one slide. So there are many areas. I'll just go through some of the technology that we use for navigating or localizing or mapping the body. You, of course, I'm sure you have done through CT scans, electrocardio, so using sound waves. Of course, there's MRI, right, imaging. And then, of course, there's fluoroscopy, which is X-ray, right? So essentially, you send a signal through the body, and due to how the signal responds to the body, you get a response. And from there, you see what's inside your body. It's a very, very traditional way of doing it. Unfortunately, I'm sure you know that all these equipments are very expensive, very difficult to maintain. Right? Okay, so that's one way. Another way is to, if I can't see inside, I will put something inside so I can see inside. One common way is now you can do is you swallow a pill, there's a camera, and actually you can see what's happening inside your body. So if you have an ulcer in your intestines, rather than opening you up to see what's happening, you can swallow a pill, and this pill will navigate through your intestines, take a photo, and it gives you the diagnostics without opening you up. Right, so one option is, instead of opening you up or imaging through, we just put a camera inside. Obviously, we cannot use a camera to look through your body because cameras do not penetrate the body, but you can put a camera inside and look inside it. Right? That's one way. If that cannot be done, there's another one called laparoscopic procedures, which is essentially keyhole surgery. Essentially, you make the smallest insertion possible, and you go through that hole to make to put the camera in to see what's going on. Right, you guys have a nice Da Vinci system. I just saw it downstairs. Very nice. I don't know, is this parked there? $1 million machine just parked downstairs. I thought it was quite amazing. But you can actually do a lot with the Da Vinci system. Right, so that's one. So that's the thing. Then of course we can actually do some interesting guidance systems. Right? Here we have a system where you want to actually use a catheter that goes through the body to go all the way to the heart. So you don't actually go to the heart from here. You go through the veins from the body all the way up. And the picture that I just show you here is actually a sensor. It's actually a sensor that receives signal from beyond. It's just like the outside has a lot of GPS satellites, and this is like a satellite receiver, and you actually receive where you are in the body. Right? So you can actually track your instrument as you are inserting into the body. Right? So another one, of course, is using ultrasound. So this is using an ultrasound probe. Obviously, if you can see the signal here, it's not that great. So ultrasound is much safer than X-ray, but the problem is the resolution is not great, and you cannot penetrate past a certain distance. That's the way ultrasound works. Right, so this is actually used to actually target the vessels, and then you can shoot the needle in to target it exactly. So the problem is when you actually do this, most of the time the nurse or doctor will actually do a few times to get it correct. This one allows you to actually do that in one single pass. Right? So I just want to summarize what we have seen. Right? So technically, you can actually break down into three parts. One is called imaging, which you try to image what's inside. Second is you do some optical navigation, either by putting a camera inside or finding a way to put the camera all the way in. And the third is, I'm going to tell you more, it's about using electromagnetic waves for tracking. So magnetic fields is a type of electromagnetic wave. Right? So something I'm sure you have known is the Earth is one big magnet. And we have been using this magnet for localization for centuries. Right? So I don't know whether any of you have used the actual compass, but it actually tells you where it's north. Right? So essentially it's a single sensor that tells you directional information. To extrapolate, if you were to allow more than one sensors and actually now measure the active field, remember, a compass doesn't tell you the magnitude of the magnetic field. It only tells you the direction. But if you actually add this information, you can actually do what we call electromagnetic tracking. It's essentially how many medical devices work. So I will tell you how most of this work. What we have here is actually a field generating system. You generate a field around a body of area, right? And then you move your sensor in this field. So typically, to make the system resilient to noise, this signal will be AC. Right? So even there's noise, you can actually pass it out easily. So once you are in this field, because this field is unique, just like a GPS signal, you can actually determine where you are in this field. Many, many tracking systems available in the medical domain run on this principle. But what I'm going to show you something very interesting is actually a flip, or what should I say, the reverse of this. It's actually you, instead of moving the sensor, you will move the source. So I flip this problem around. Right? So now instead I have one sensor, I have many of them. Right? When I have many of them, now I don't track the sensors, I track the source. And here I can have a magnet and I can go around. Essentially it's the same thing, but I flip the idea. So there are many advantages, and of course disadvantages over this and this. But essentially they are the same concept, using fields to determine where you are. Right? So if you want to buy a system today, you can actually buy many of these systems. But they are essentially active magnetic tracking systems. Essentially, they have a big field generator, large systems that generate field. And you have a nice small sensor probe, which is electronically tethered. You can connect this to any instrument. Can it be a forceps, it can be a catheter, and you can track this system within this field generating unit. Right? So this is active. Right? So I'm going to show you more about passive magnetic tracking system, which is this system here. Right? This system, this approach is very advantageous for a number of reasons. One is, firstly, the thing that moves is no longer powered. Right, previously, this guy here needs to be powered, because without power, the sensor does not work. But now I'm not going to move the sensor, I'm going to move the source. And I'm not going to move an active source, I'm going to move a permanent magnet. And the nice thing about permanent magnets, if you have tried it, it doesn't require batteries. It actually generates its field passively. Right? It's one of the few things in nature that it has energy that's emitting all the time. Right? Similar to like radioactive, is similar to that. Right? So I don't actually need to power the source. Right? So when I put a magnet to anything, there's nothing tethering to it. That's a nice thing about it. And of course, magnetic field has many great applications, good pros. One is, of course, it's actually invariant to many environmental factors. Temperature, pressure, radiation is actually not affected by it. So very nice. So you can put in all kinds of harsh conditions and it will work quite well. Second is that I'm sure you have seen magnets do not require contact. You don't actually need to touch the magnet to get the field. It will actually in magnetic field right now, but the Earth magnetic field is quite relatively weak. But nevertheless, you are in a field right now. And of course, magnetic field, like just as any other electromagnetic waves, propagate at the speed of light. That means when you send something, you actuate something, there is no lag. Compared to mechanical systems, we have mechanical lags. Right? And nowadays, with very advanced sensors, the bandwidth of the sensors are in megahertz. Right? So you're not limited by any, you actually track very fast things that move very quickly. Right? So there's a lot of potential. Right? Just that this area is what I would say not as fast developed as this area. Right? But maybe in the next 10 years, this will change. Right? So this is what essentially what passive magnetic localization is and what it entails. You have a sensing assembly that is stationary, most of the time stationary, and you have something that moves that you want to track. One thing you can think of is perhaps this is the body is here, and you want to track a catheter going into your body. Right? That's one valid thing. So you actually will put this magnet into the catheter, and this guy will be on the body, and you can track it all the way through. Right, so these are the four things that actually affect the performance of this system. One is, of course, the inverse algorithm, the noise, the field modeling, and the sensor arrangement. I'm not going to go through all, right? But I can tell you this is the current state of the art. And I've actually advanced in all of these aspects to improve the performance. There are too many here, so I'll just choose a few of them to show you what are the interesting things that we have done. Right, so one thing is, I'm sure you have seen when physics, when you learn about magnetic fields, you learn about this cool equation called the magnetic dipole model. It's a very nice equation, very simple, and works most of the time. What they don't tell you in the textbooks is that this model has a few limitations. One is that it assumes that you are quite far from the source, relatively far. Okay, that's one problem. Second problem, this model does not accommodate or include any provisions to the geometry of the source. Right, so this source can be cylindrical, cuboid, spherical, and the equation is the same. But as you know that the magnetic field will be different. Right? So what I've done is actually to develop a new field, because we find that if this field is not great, whatever I do to localize will be bad. Right? So I need a good field. So what I did was first actually to experimentally measure what a real field will be. So I got two magnets, one cylindrical, one annular cylindrical, means it's a cylindrical with a hole in it. And what I did was to actually use a system to measure the field, right? And then I actually tried to map it to this dipole model and see how good, how bad this model is. So I just plot the error here, right? You can see the error goes to 200. 200, like the value that's overshooting is under approximating or overestimating the field. And you can see most of the error occurs near the magnet. And this is to expected because this equation that we use, the magnetic dipole model, is used for far field projection. Once you go very close, right, relatively close, this model is no longer great. Right? So the problem right now is actually how to develop a new, there's a lot of high error. How do we improve this? Because once you have high error here, when you do localization, means when you measure the field and determine where you are, you're going to have high error too. So if you're trying to be in New Zealand and you actually try to use the system, it will actually tell you you are at the South Pole. Or maybe worse, you're at the North Pole because of the high errors in the measurements. So the next step was to actually improve this modeling. And there's some requirements because when you do this modeling, you want this thing to be real time. Most of the time when you actually do medical tracking, you cannot wait 1 hour for you to get the estimate. You need it real time. Right? So we actually try to use ANN, which is artificial neural networks, to actually improve the modeling. So essentially what we did was to, instead of using that model, the dipole model to estimate the model, we actually will fit the experimental data to this ANN model and see how it goes. And this is the result, because after that, the errors are much smaller. Right? The errors are much smaller. And when you do tracking performance, this is using the old dipole model. This is using the neural network model. So you can see the tracking performance is much better. Right? But I'm sure if you have done neural networks or used neural networks, you know one problem of neural networks is that it's only good in the area that you train it. After that, it actually would work actually quite poorly. So this is the dipole model, right? This is the neural network model. If you were to extrapolate and try to do tracking outside the domain where it was trained, it would be very bad. Right? So this is one of the key limitations of the neural network model for magnets. But it's okay. With this, I thought this is good here, and this is good here. So what it is, why don't we just combine the two? Right? So here we have what we call a hybrid model. A hybrid model where when you're close to the magnet, you will use the ANN model. When you're far away from the magnet, you use the dipole model. And because there's this two modeling, we have a transition system that blends the two using a sigmoid function so that your transition between two models are smooth. Right, so this is what we did. You can show this is the dipole only, the neural network only, and this is the hybrid. Right? So this is the performance. You can see that before that, the dipole model is very bad. Once you do the neural network, it gets better. But once you actually do the hybrid model, it gets even better. And the reason is because now the ANN doesn't need to map the entire workspace. It just needs to map very close. So the performance is actually better for the solid case. Of course, the annular case is got slightly worse because of the harder geometry, right? But as you can see, much better. And you can see here it's so bad. So when you're using a dipole model for something that is not cylindrical, it gives you a very, very bad performance. Right? But the improved modeling will actually improve it quite well. Right? So this is what we can do. So you can do tracking and stuff. Right? So once you're here, this is more of what we call lab stuff. Right? Then you're thinking, what can we do with this? I can do tracking, but what can we do? Right? So that's where we try to motivate with medical problems. Right? So I worked with a doctor from Mass Gen when I was in MIT, and they have this procedure where they needed to insert a catheter into the brain. Okay, inserting a catheter into the brain. Right? So this is essentially going this and going all the way to the ventricles. And the reason for this is because perhaps the brain is there's a rupture in the brain, and you actually need to relieve pressure. This is one of the most common procedures a neurosurgeon would take. As you can see, this is a very dangerous procedure. If you make a mistake here, the guy might just perhaps not see, not move, right? If this tube goes into the wrong location, right? So it's very dangerous. Unfortunately, I don't know, or fortunately, this procedure is done blind now. If you go to any hospitals, the neurosurgeon that does this is going to do this blind. And when you do something blind, it's not unexpected that you might need to do a few times. And it's reported in literature that many neurosurgeons will take more than one pass to get it right. So insert it in. Oh, I did it wrong. Put it out and put it in. Because unfortunately, that is the procedure that they have to do it here. Right, so of course, that results in many complications over the years. So there are a lot of problems that's reported in journals, in medical journals of this problem. So again, the problem, why is this happening? Is because every pass that you do that's unsuccessful increases damage to the brain. Because your brain is like jelly. You know? Once you put something through it, you're going to move some stuff around. And as you keep putting things down, putting multiple insertions, you're going to damage the brain more and more. But unfortunately, because that has to be done, because right now you need to actually do that to save the patient, right? So that has to be done. But the point is, we're trying to see whether we can reduce the damage as we are doing this, right? So this is the system that has been used in MassGen. So they actually use electromagnetic tracking systems today. But what they've done is quite difficult to use because firstly, the body needs to be fixed to the bed. Then they have actually placed a few generators here. So as you remember, if this is a tracking system, everything must be rigid. You cannot move, right? Because once you calibrate the system, if the body just moves by 1 centimeter, the whole calibration is off, and you have to recalibrate. So you can see it's very cumbersome to do this, right? So once they do this correctly, then they will actually do the insertion. Most of the time, there is no time to do this. If somebody is in danger, when the brain is bleeding, there's very few time to do this calibration, putting a person there, right? So we're trying to think of, is there a faster way of doing this? But retains all the advantage of electromagnetic tracking. And this is where we come up with a passive magnetic system. So instead of using active, remember this is active field. So this 3 devices creates a magnetic field. And then the catheter will have the sensor. So now we still do the same thing, except now the sensors are around the body, the head. Right? The magnet is in the catheter itself. Right? By doing so, there's a lot of advantages. First, this catheter no longer has any wires, because previously you would need to actually power the sensor. That's one. Secondly, now the head is free to move. You can actually adjust the head because the system is actually attached to the head now, because it's more compact. There is no field to be generated, because we just use the field from the magnet. Right? So, and an interesting thing is when we did this, as you realize here, this pattern is not regular. Right? It's actually not regular, and it's actually designed such that it's not regular, because an ordinary or regular placement of sensors is actually worse performing than one that is irregular. So when I say irregular, it's actually optimized by a genetic algorithm. So we essentially actually let this whole place to be free, and we actually put sensors until we find the best performance. Right, so actually the best performance is not something like this, but something more haphazard like this. Right, so these are some of the results where you can see if you were to design the sensing assembly more, it has more effect on the performance than adding more sensors. Right, so 6 very well placed sensors does just as well, if not better than 10 randomly placed sensors. Right, so when we do this, I showed that designing the sensing assembly is very important. Right? So to verify how our performance, obviously we don't use our hand because our hands are not repeatable. So I use a robot actually to do the experiments. But here I would like to show you the video here, right, of the actual system here. So you can see here, plus it's connected to a GUI which actually tells you where you are live as you're inserting it. Again, this thing has no wires, it's contact free, and just by measuring the magnetic field. So essentially you can think of it as truly like magic, right? But the magic is the math behind this, right? And understanding the physics behind it. Right, so this is ventriculostomy, means inserting a catheter into the brain. But of course, this is not the only procedure in healthcare that requires inserting a tube in the body. This is a more common one and affects much more people around the world. And this is actually inserting of a nasogastric tube. So nasogastric tube allows people who cannot eat to actually have food inserted onto the stomach. Or perhaps you have something in the stomach and you want to aspirate, you actually use a feeding tube. And so many, many things. Again, this procedure, I don't know if anybody have tried this or went to the hospital and had it done. It's done blind. You push it in and you hope that you get to the stomach, right? And the problematic area of this insertion is that if you drive, right, this is a Y junction. At this point, your nasal cavity goes into the esophagus, which is the correct place to go to the stomach, or the trachea, which goes in the lungs. And that's very bad, because if that tube goes into the lungs and you release feed, you drown the patient immediately. Right, so it's very dangerous. So in Singapore, once we actually insert the tube, you must go through an X-ray to verify that indeed the tube is in the correct place. So these are two error places, one going to the lungs, one coiling. Means it goes in, but it does some merry-go-round and doesn't go to the stomach. Right, both are undetected as you insert it. You will not know, especially if the patient is unconscious or not responding. Right, so you will actually not know. So again, no feedback mechanism. So as you do it, you will not know. You will only know after you do the X-ray. So this X-ray is quite good. It actually tells you whether you're doing it wrong. But it doesn't tell you at the point that you're doing it wrong. Means you could have done this incorrectly, wheel you to X-ray, find that you did it wrong, and have to do it again. Right? So I don't know whether you want to try that, but that is the procedure. Right? And interestingly, in Singapore, this procedure is about $100. More than 50% of this cost is just because we need to X-ray you. The tube is 50 cents. Of course, the pay the doctors and the nurse is some cost, but by and large, most of the cost is to the X-ray. And again, not every place especially nursing homes, do not have X-ray. Right? So this, if you can find a method that doesn't require X-ray, it's real time, you can eliminate a lot of these issues, plus make it cheaper. Right? So again, along the same road, we actually developed something similar. We have a system that targets the neck. Right? And again, we have a system that magnetic sensors that wrap around. And again, the tube here, we actually insert a magnet. Nice thing about doing is once we insert it, we can forget about it. There's no need to bother about batteries. There's no need to charge this guy. Once you put it in, you can actually put it and forget. So this system is very simple. We just 3D print this thing, and there are like 11 sensors here. Right. So we actually pattern this and stuff. So I'll just show you some interesting videos. So this is actually an engineering video. So this is the system, and this is real time. I must stress that this is real time, because some people think that this is not real time. I computed after. No, this is actually real time. So you can see as we move the magnet, we can actually localize. So if you're looking at this is actually the throat area, the esophagus, and the trachea. So we're trying to see whether we can actually differentiate and what accuracy we can get. Right? So we can actually go down to pretty good accuracies, millimeters, which is more than sufficient for nasogastric intubation. Right? So this is where we have it testing. Right, so this is the frontal view, and this is the top view of the system. Right? So then once we got this to work, we wanted to test in an actual model of a nasogastric thing. So we got this model is actually used by nurses to practice NG tube insertion. And here, maybe the video is not so good, but you can see the tube going in. And once you got into range of the system, you can see it live. So if you were to insert this and you find that you're going to the wrong place, you can stop immediately. Right? You don't have to wait until you finish to stop. Plus, if you were inserting and it coils around here, which is common, you will know, because you were inserting, but this point doesn't move. Right? So a lot of things that you can detect by just measurement. Yeah. So this is the video. So the next thing we did was to test it in a biological environment. So we went out to buy some meat to test it and see whether it actually works in a biological setting. So no problem, you actually put a metal object, because most people say, what happens if you put a metallic objects? Yeah, I tried it with the metallic objects. It does affect it, but because of the algorithms we employ, we develop, it's immune to metallic objects nearby. So we tested this. Right, so once this is done, we thought, what's the next step? We've done engineering tests, we've done biological tests. So the next logical step is to try to test it on a person. No, it's not. Of course, it's not. That's not the correct way yet. Next step is actually to try to test it on cadavers. But before that, let me show you what else we also did. So as you know, all your necks are different size, right? As you can see here, this prototype that we developed is rigid. your neck, my neck's different size. So what happens? Well, how about if you need to do it onto a child? And the child's neck is not going to be like this. So what we did is actually to develop a prototype that can blend. So we 3D printed a structure that has bending structures that can allow it to conform. The problem with this development is now that the tracking system has moving sensors, which nobody likes. So what we did is actually to put the flex sensor so that we can determine how much the assembly has changed and correct for the algorithms. Because for this algorithm to work, we need to know all the locations of every sensor precisely. So this flex sensor allows us to correct for it nicely. Right, so once we've done that, the next thing is to test it into a cadaver. Again, this is not a real person. Technically, it is a real person, but it's not a person that's alive. So we actually went to Thailand with a doctor there to do a cadaver trial. Right, so this doctor here has never seen our device before, and he's actually going to try to do the insertion with our device. So you can see our device here. I think I'll show you another picture here. So here is the device here, the GUI connected to our system. This thing is actually fluoroscopy so that we can image the system as we are going through. Because we need to know as the person is inserting where the tube is in real life. Right, because we can determine where it is here, but we want to verify that it's indeed in the correct place. Right, so we did this cadaver trials. Right, so here you can see him looking at the GUI, and here's the fluoroscope scheme just for confirmation. But he's not using this. He only uses this to do the insertion. Right, so I think here I have a video. Yeah, I have a video here. So you can see there's the tube. This is the tube going down. Right, and then the GUI is live here. So you can see it provides, of course, I'm sure you'll be aware to tell me that here you can see the organs, the neck. My system doesn't allow, but I think we don't actually need to know where the neck is. We just need to know that the tube is actually passing through the correct location, right? Because magnetic fields don't actually allow us, this method doesn't allow us to image. It only allows us to track, right? But it does a pretty good job of tracking the tube as it goes into the body, right?
How do you know if it's going the wrong direction?
Also, you can actually track the history. Yeah, you can see the history. Yeah, but most of the time, if it's going the wrong direction, it means it's coiling. So you should pull up back and try again. Yeah. So as you insert in, there's usually only one way to go down. There's only down. You can't actually go any other way. And this part is quite, the road is very, very straightforward. Once you get to here, it's a Y junction. You either go into the lungs or you go into the stomach. And once you pass this junction, it's almost clear way. There's less. The major accidents, if you wish, happens here at this point. So that's why we target this point specifically for this. Right? So that is a medical device. So I thought maybe, yes?
So is there an obvious change in direction
yes.
that goes down that can be seen by the doctor?
Actually, we try to not, once it comes here, it's a bit too late. We want to actually determine the change in trajectory right here. And the esophagus is actually in front, sorry, the esophagus is behind the trachea. So your windpipe is here, the esophagus is actually behind it. And there's the difference of 1 centimeter that divides these two. And once it comes to let's say you go to the trachea, it will split either left or right to your lungs. So this part is very detectable, very easy to detect. But we're trying to detect it right here. Right? Because if you want to stop it, you want to stop the damage, you want to stop it here rather than here. But you can detect it anywhere on the body. Yeah.
Sorry to continue. If you don't go down both, how do you distinguish between them with yours, especially because it's such a tight spacing?
So what I didn't show here is that we have one here, and we have one more at the stomach. Yeah, it's one more confirmation. For confirmation that we have reached the endpoint. The problem is this system here, because of the magnetic field, is too far. So you need a separate confirmation system here. The range for passive magnetic field is, unfortunately, compared to active, it's shorter range, which is about 20 centimeters. So you can actually track the body, but just need more sensors. And nowadays, sensors are pretty inexpensive. You can actually, technically, you can build a vest, wear the vest, and track the thing through the whole vest. But because there's a cost to it, you want something that's easy to use, relatively inexpensive, and can be used quickly. Yeah. So we actually suggested a vest. I told the doctor, hey, how about you wear a vest? No, the doctor said, no, I don't want my patients to wear a vest. It's too troublesome. We want something easy that you can put on and go off. Yeah, so we considered many variants for this. Yeah. And then if you remember the screen, he told me after a while, I don't need to see the screen. Can you just tell me a green light that I'm doing correctly? So actually you can illuminate the screen and have the lights here and just saying you are doing a good job, or red, something is going wrong. Yeah. So very interesting. Once I talked to the doctors, they changed the design quite a bit. Yeah. Yes?
How is accuracy?
Accuracy for this is millimeters. Millimeters. Yeah, and yeah. So for this application, it's more than good enough because the difference between the esophagus and trachea is more than 1 centimeter, more than 1 centimeter. Yeah. Right, so I just done 2 medical devices, so I was worried that if I do all medical, it's really boring. So now I try to shift gears a little. So here's something a bit more interesting. So here we have a, I'm sure you've seen this, a robotic cheetah, right? They're trying to mimic a real cheetah, right? The difference between this robot and many robots that can run is that this guy is supposed to go at high speeds. And I'm sure when you run, it's very important that you feel your feet. I don't know whether you know that, but when you run, if you cannot feel your feet touching the ground, you cannot run well, right? So when the first robot was developed, there was no sensor here. So there was some limitation of how fast you can run, right? And this requirement for this sensing is very tough because this guy, when you run fast, the forces are large, extremely large, up to 1,000 newtons, right? And also we have to measure shear force because when you walk, it's not the normal force that you're trying to determine, but it's also the shear force, so that you know whether you're slipping or not, right? So as you can see, we also want this system to be lightweight. It cannot be heavy, right? So there are not many devices, or should I say, at the time when we developed this, there were no sensor that can do this, nothing. You can buy a force torque sensor, but it's going to be big, plus it's very fragile. Most force torque sensors, if you drop it, that's the end of the force torque sensor, right? But here you can see that this thing will be impacting the ground many times a second at high speed. So I tried to thought of a way to actually use magnetics to solve this problem. And what we did was to use what we call a magnetoelastomic force sensor. What it does is we actually have a material that conforms, and by measuring the deformation of this material, you actually infer the force. Right? Sort of like a spring. When you actually compress a spring, if you measure the deflection, you can measure the force that's applied. So it's more like a transducer. But the point of this is to measure the deformation of a material is quite tough. You can think, okay, I can use a camera. I can use a laser interferometer. Yeah, you can, but you can't do it on an actual robot. It's not robust enough. It's too fragile. So what we did is actually I'll show you the graphic here. So to have sensors and a magnet. So this is actually touching the ground. So the thing that touching the ground is the magnet. That if you were to compress this, because of this silicone post, it will conform or deform. You can deform normally and deform shearingly. So when this plate moves, this magnet position is measured by this system. The nice thing is this part that touches the ground has no electronics. And again, because magnets do not require line of sight, this sensor doesn't even need to see it, right? And you can actually, this system is all solid state. There is no moving parts. So when actually you use this on the actual moving system, it's very robust, right? And this, as you remember, and I said, magnetic fields operate at the speed of sound, the speed of light. When this thing moves, there is no lag in the measurements. It's literally real time. Right, so we actually developed a system, we do the modeling so that we measure the forces. So we actually couldn't find a system that can provide enough force, so we used a milling machine to provide the force. Right, so we find the correspondence between the deflection and applied force. So from there, we can actually compare some modeling difference. So traditionally, what happens is most people will actually try to calculate it cascading. It means you try to measure the change in magnetic field and determine what is the deformation, and for the deformation, determine what's the force. This is a traditional way of doing it. What we have done in my approach is we will bypass these two methods, because as you do this, you get one error. Then when you do this again, you get this same error compounded by another error. So essentially, you have two cases of error that compounds each other badly. So what we did is actually from here, we developed a model that actually comes all the way here directly, bypassing the need to actually determine the actual deformation, because that's not important. I don't really need to know how much this thing is deformed, but I just need to know how much force is applied. So this is the system that we did, right? So you will see the actual system. So this is when we actually apply the arbitrary force onto the sensors. So you can see it tracks pretty well. Of course, there are some difference. So this is the real force applied by measured by a real force torque sensor, and this is the estimated force. In the normal direction, so this is the normal direction, it's not that great. Can you see some? This is due to the creep effect of the material. Because once you compress the material, it takes time to settle. And this is it trying to settle. Right? In the shear direction, it does quite a good job. Right? So you can see we can go all the way to, we didn't go to 1,000 because we were afraid it would break it, but it goes up to 400 newtons. Pretty good for something that's only 20 grams. Right? Something that's 20 grams, I can measure more than 400, almost 400 newtons of force. Right? 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 So next, the last example I'll show you today is going to aerial robotics. So previously, we have seen medical device using magnetic fields for positioning. And then I'll just show you, we can also use magnetic fields for developing a novel force sensor for a running robot. So next, I'm going to show you that we can actually use magnetic fields for aerial robotics. To motivate this a little more, I will have to show you something interesting that I'm sure you have seen nature-inspired aircraft, right? Like UAVs. I'm sure you've seen flapping wing UAVs. Right? What else? Flapping wing UAVs, right? So other than insects, birds, that gives you inspiration of flight, actually trees actually have a very nice way of achieving flight. Just that most of us do not actually see it. The maple seed, which it looks like this guy here, when it falls, it rotates in a spinning manner, right? The reason why I put the angsana seed is because in Singapore, we don't actually have this maple seed. We have some a cousin of the maple seed, which is called the angsana seed. It's a seed with a wing that's all around. It has the same process, but of course, this guy has a nicer rotation motion, right? So this rotation motion can be harnessed to develop a UAV, which I will show you here, right? I think I need my mouse here. Right, so I will show you a video of a nature-inspired UAV. How the magnetic field comes into play, I will show you soon. But I'm wondering whether you can connect it before I tell you. So again, this system is essentially a seat with a wing. But for us to achieve flight, we need to apply energy. So here we have a propeller that tries to induce rotation. And then we have a flap here that rotates so that we can actually we can control the pitching motion and rolling motion of the UAV. So here is the fabrication. I think this part is a bit boring. I'll skip ahead. Too much. Sorry. So here is the UAV taking off. So it actually spins. And once it achieves a certain RPM, it has enough lift to lift off. Right? And then you can actually bring it to left, you can roll left, roll right, go for gain altitude. And the nice thing about this platform, if you were to lose power, you actually rotate to the ground. Now my question to you is, do you know where the magnetic field comes into play? Right? So maybe a hint here. So most UAVs obviously do not spin like this, right? I don't know when you realize when you're spinning here, have you tried spinning around before and trying to walk? The problem with this is I think I'm trying to motivate you to do is I don't think you know where's the front anymore. Because when you are spinning, this craft has no front. No, as in traditionally there's no front. Or essentially, should I say, every part of the UAV is the front. Right? The problem right now is when you have no front, it's very hard to control something where you have no form of reference. Right? There's no form of reference for this craft for it to fly. But how does it able to roll left and roll right? Right? Because without something that I've been talking about for the past 40 minutes, this flight would not be possible.
So are you using this magnetic field?
Yes, I'm using the Earth magnetic field as a reference point so that the craft knows where's the front. This is not new. I'm sure you know birds use this so they can go for migration. Right? That's how they actually determine where to fly, in which direction to fly. In the same avenue, this craft uses the Earth magnetic field, which is present everywhere on Earth. Of course, if we were to go to the moon, maybe this will not work. Right? But as long as you're on Earth, this will work quite well. And of course, if you're on the North Pole, maybe this will also not work too well. But by and large, I don't think we will fly anywhere near the North or South Pole for now. Right, so this is a nice motivation for how magnetic fields can be used for aerial robots as well. Right? Yeah, so I just wanted to, since I'm already here, I'll just talk to you about my very interesting follow-up. So this is what we call the Mooncopter. Mono means one wing. Right? So the nice thing about this platform is it's very efficient because it uses wings for lift and not rotors like multi-rotors, like drones. Right? So the problem with this platform is it doesn't fly far. Right? Like most helicopters or most rotor-based craft, you cannot fly far. But you can resolve this by putting two of these together and merging them. And we call this the THOR, a transformer hovering rotorcraft. So, hey, wrong one. I used the wrong video, sorry. This video. Yeah, so this is a craft that we developed that builds on the two single rotorcraft, but we merge them together. So again, it has two wings that are now not orthogonal, but parallel to each other. So you can fly the same way. Again, we still use the magnetic field for us to reference, or else we will not be able to roll left, roll right, and such. But it has a very interesting way of a new flight mode that we can develop because we have two wings. If you were to rotate the wings, we can actually transform this craft into a normal fixed wing craft, which is the most efficient way of achieving flight. Right? That is the reason why nowadays, to go long distance, we use a jet airliner and not a helicopter. So you can actually transition and go to fixed wing craft. So essentially, it's a real-life transformer. Right? So once you get to your destination, you don't need a runway. You can actually transform back to a hovering mode and land. Right? So this is, I thought, a nice motivation for this. Right? If you're wondering why would you want to design a craft that perpetually spins, right? Here is the reason. So if you compare to a normal UAV, about 25% of the body generally, the rest is weight or aerodynamic drag. This system, where we actually have the body here, generates most of the lift here. So as you can see, if you compare these two guys, if you have the same weight, same strength, same dimensions, this guy will fly much longer, purely because of the efficiency point of view. And the nice thing about the THOR is, whenever it's in both flight modes, both of the flight surfaces and control surfaces are in use at all times. Most UAVs that are hybrid today have separate propulsion system, separate aerial control surfaces, such that when you're in either modes, some stuff are not in use. So you are something like this, where you have actually increased more drag or weight. But this system is very efficient. And I think it would be nice to benchmark our design to nature. So here I have a graph that maps out how this monocopter is compared to nature. So first thing I did is I compare it to all kinds of rotorcrafts. Right? So here you can see helicopters all the way to direct lift fan. So this is like the F-35, the Harrier jump jets. So these crafts are very inefficient because they achieve lift by using a very small area of force. Of course, the helicopter is actually one of the most efficient. Quad rotors, like this guy here, are somewhere here. The monocopter is here and has the potential to go much higher. This is one way. Another way of thinking of it is checking the wing loading. So here I have actually a graph that highlights many common birds and insects. As you can see, nature has a way of lining up here. Right? So there's some relationship between a mass of a body of a bird or insect to how much wing force it can generate. So normally it's this way. Right, so obviously you want to try to go as close as line as this as possible. A quad rotor, a drone, is somewhere here, and I did not draw it incorrectly. It's outside the graph. Right? So it's actually not very efficient. Right? The monocopter prototype is actually here. So it's very similar to like ducks. The power efficiency is very close to ducks. Right? So anyway, this is a little off topic, but I thought it would be interesting to share about that. Right, so anyway, I just wanted to show you some interesting thing that I've done. So I showed you passive magnetic field, which are very great. I truly believe that passive magnetic fields can be actually used widely, much more. Right? And I show you in medical technologies, you can actually use it. You can use it in robotics. You can even use it in stuff that fly. So with that, I'd like to end my talk. I think I talked for quite some time. Yeah, so I'll be happy to take any questions that you might have from this. Yeah.
Thanks, Shaohui. Any questions?
You're talking about the device that you use for observing things in your brain, the pressure things. You mentioned that the active systems have to be calibrated.
Yep.
Does the passive system, because everybody's head's a different size, also need some form of calibration?
Yeah, so the passive one is easier to calibrate because I designed it such that you can actually put it on the patient's body directly. The goal, I didn't, because it's too much to present. The goal was actually to stick the system onto the patient and have the patient go through a CT scan. Because before you do any insertion, the patient must go through a CT scan.
Right, okay.
So when we do the CT scan, my goal is actually to do the calibration as the CT scan is done.
Yeah, okay.
Yeah, but you cannot do it with an active system. You cannot actually, you don't view the entire EM system and do the CT scan and things like that. But for something that's small, you paste it in, you can do it quite quickly. Yeah, so that was the envision of how the workflow will suit. So as you are doing the CT scan, the calibration will be done. So once you come out, you're ready to do the insertion immediately. Yeah. Yes?
Could you extend your you sort of have a slice snapshot in position, but you could maybe rotate your cuff elements a little bit to get a little bit of a view.
For what are we talking about? For
Like imaging for insertion of catheters in the brain, you know.
yeah.
You could potentially, now you sort of have a slice view. You could maybe image back and forth a little bit, or no, sorry, that's more for the cuff around the.
Oh, you mean this for the nasal tube? Yeah.
Just to get volume information.
So this system here is actually not line based. It's actually field based. So when you actually put it here, you're actually tracking a 3D volume, not a 2D line. So as you're going in, it actually tracks a 3D volume in this part. Yeah. So it doesn't. We don't actually need the position accurate. I just need it here. The actual position does not matter. Yeah. So it's not like a line sensor. It's more like a 3D cloud sensor, if you wish. Yeah.
I guess the question is then how deep or how high in line does it go away from the midplane?
So we can go like 4 to 5 centimeters, 4 to 5, and it's good enough to cover before and after, because most of the bad things happen here, right here. Yeah. Yes.
As you know, currently the surgeon using the navigation system that is based on the visual tracking. Do you think that your passive magnetic tracking will be add-on on that, or will replace this technology at the moment? Because the navigator system is tracking the rigid instrument, not flexible.
Yeah, so I think there's always a role for vision-based tracking, because vision-based tracking is very accurate. The problem with vision-based tracking system is in certain applications like inserting a tube, you don't really want to have a camera system to use this regularly, because something like inserting a tube is very regular. It will be done like almost every day. But if you want to do a specialized surgery, I think an optical system is much better. Its accuracy is better and stuff. But again, for optical-based system, the only problem is that occlusion is a problem. You cannot block the line of sight with the camera. My hope is for the technology here is I hope you can actually use it in homes. So when you actually, not in your home, but like nursing homes where there's no X-ray, no advanced medical facilities, or perhaps do this at the field, medical field, on the field where there is no equipment, but you need to insert a tube into the body. So this will give you at least better than anything that is available right now, accuracy that's required to do it safely and confidently. Right? It's like the GPS. As long as you can tell the doctor or person doing that he's doing a good job or correct job, his performance will be better. It's always like that. Yeah. I'm trying to give the person who's delivering this healthcare or this procedure as a good shot as possible. It will not be better than, of course, X-ray, right? Of course, X-ray or fluoroscopy, but it's sort of in the middle ground. It doesn't require very expensive equipment. It doesn't require a lot of power. It can be done in the field. You can do it here. Yeah. So I think I'm trying to focus on a different target. I don't think it will replace many other technologies, but it has a place in certain places where many of the technologies where you just talk about it's not easy to use, hard to use, or expensive.
I have a question.
Yeah.
Previously said that one of the advantages of this passive sensing is that it does not have to be tethered. And in a specific example of the nasal tubes, it is tethered because you need someone to kind of insert that thing inside. I was wondering whether you can really remove the wire so that you can kind of actuate this passive object.
So there's no wires. There's no wires.
Okay, and
Yeah.
then without wires, is it possible to kind of actuate or move this object around inside the body?
So it definitely is possible. But when I talk to many of the clinicians, I think most patients and doctors prefer that this is done with a human. Yeah, for many of these applications. With a magnet, actually, you can actually do it automatically. But I think for such a simple procedure, it's more of, now we're trying to just help it such that you can do it in one shot. Because right now, you might require a few shots to get it done. You definitely can make it fully automated with the correct tool, because it's a magnet. And the magnet is actually essentially a motor. Right? For now, I just use it as a sensor, but you can use it in an actuator as well. Yeah, definitely can. But I think when I speak to many doctors, they're not ready, or should I say, they do not welcome that method of usage yet. Yeah.
You were talking about the cheetah force sense. So you were saying, I wasn't quite following exactly. You were saying in the slide about 2 steps versus 1. So it's the 2 steps to look at the depression of the material and then relate that depression to force, is it?
Yeah. So here, if you imagine, if you were to deflect, compress this thing, the material will compress and the magnet will move relative to the top plate.
Yes.
Right. So the idea is, traditionally, the idea was to first determine where the magnet has moved. Right. Once you determine where the magnet has moved, you try to determine, to achieve this motion, what was the deflection that causes this. So you have 2 models that you go through. One, through the magnetic field model to get the deflection or position of the magnet, and from there to infer the deformation that caused this. So there are 2 models at play. So rather than because we tried it doing the cascading method, the error is quite high because of the 2 models inaccuracies. So we actually developed this, because I don't actually need to know the intermediate step. This information here is pointless for.
How do you jump the step?
So I didn't really jump the step, so we actually do a modeling with a neural network. So we actually use this to actually measure all possible workspace and use the data to map.
So it's kind of like a big lookup table.
It's essentially a nice big lookup table. Yeah. Yeah. So that's the bad thing about it. But the nice thing is it works in real time, which is very important for such applications. Because this model can be quite complex too. If you actually use a complex model, this inverse computation can take much longer than is required. And when you're running, every millisecond counts. Yeah. So for this application, we actually, yes, we use a lookup table for this.
I think, any more questions?
Sure, sure.
There's a company here in New Zealand that uses the Earth's magnetic field for magnetic resonance imaging of small objects. Do you do any work in that area?
So I don't have, but my colleague in SVD does. So what she's trying to do is to use permamagnets for MRI. So MRI right now, you use heavily energized, high, like I think 14 Tesla system to get imaging. You can still do the same thing with permamagnets, just that the resolution will be not as good. But the nice thing of having a permanent magnet-based MRI system is that it's very portable. You can put it in your pocket and go. Yeah. So I don't do it, but my colleague does this thing. Yeah. So definitely it's an interesting area, because if you can have a pocket MRI in your pocket, yeah, that's pretty cool.
Okay, I think we've come to the end of the seminar. Let's thank Shaohui again for his presentation. And, and there's, by the way,